Good morning. So now this is the class for discussing driving large capacitive loads. So when the capacitance value is increased, the delay also increases. Previously we have seen the formula for the time delay. In that you can observe that the time delay is directly proportional to load capacitance, right? So the load capacitance value is increased, the delay is increased. Okay. So in general, what are the different methods we have to follow to overcome this problem? That we have to see in this class. Okay. So usually the chances for providing very high load capacitance is when the signals are propagating from the chip to half chip, approximately the capacitance value is 10 power 4 square series, greater than that value. Okay, so that much high capacitance load we can observe in the half chip as a load. So to overcome this problem, we need to provide very low resistance source circuits. That is, if you take the inverter has to provide very low resistance. Then only the total delay can be reduced. Low resistance means the L by W ratio should be low, right? For that, if you observe, L by W ratio should be low means L value up to certain level you can reduce, but after certain limit you can't reduce the L value. Okay, there is a constraint. But coming to W, by increasing the W value you can reduce the resistance. So but with reference to one stage, if you increase the W value, again the capacitance value increases, so the delay is increased. So to overcome this problem, various methods are there, like the methods which you can see now are the cascading inverters as drivers. So instead of a single inverter for driving the large capacitive loads, it is better to use many stages. And another technique is using super buffers. One more technique is using biasing mask technology. So these are the different ways or different techniques used to drive the large capacitive loads. First of all, coming to cascaded inverters as drivers. Here, instead of using one stage, here the concept is working on increasing the width. But if you use the one stage, what happens? The capacitance value again increases, so that again delay increases. So instead of increasing the W in one stage, many stages are using, but the W value is slowly increased from one stage to another stage, so that the resultant delay is less. That is the idea behind this cascading inverters. Let us see, this is the diagram for driving the large capacitive load CL. Many number of inverters we have to connect. The size of the inverter goes on increasing like this by using a width factor F. Okay, a width factor F. This is the cascaded inverters. As you know, for the 4:1 NMOS inverters case, 4:1 NMOS inverters case, the total delay for the pair is NMOS pair. Okay, for the NMOS pair equal to 5 tau. In VLSI design subject, you studied that the total delay in NMOS pair is 5 tau. Okay, how can you get the 5 tau? since the ratio is 4:1, in the rising instant maybe it is 1 nanoseconds time, whereas in the falling instant it may be 4 tau. 4 tau we can get. So 1 tau plus 4 tau. Totally the delay is with reference to pair is 5 tau. Okay. Similarly, in case of CMOS case, it is 7 tau. Okay. But here, since the width factor is f, therefore the total delay in NMOS inverter pair is equal to 5f tau. In CMOS case, it is 7f tau. Okay, you remember that value. Now, let us see how much f value we have to use to improve the speed. First of all, let us assume y equal to CL by square CC equal to f to the power of n. That means what? What is y? In the given capacitive load, how many square CGs we have? That is y. Okay, the number of square CGs in the CL is y. It is equal to f to the power of n. Where f is, you know, width factor. What is n? Number of stages. How many number of stages we have to use? Okay. Now apply logarithm on both sides of this equation. You can get like ln of y equal to ln of f to the power of n, which implies n equal to ln of y divided by ln of f. Okay. So for even number of transistors, even number of stages, even number of inverters, if n is even, the total delay you can estimate as n by 2 into 5f tau, that equal to 2.5 n f tau. Clear? Since 5f tau is for the pair, the delay for the pair. So for n even number of inverters if you use, the total delay is, we can calculate using n by 2 into 5f tau, which is equal to 2.5 nf tau. Similarly, in CMOS case, it is 3.5 nf tau. Okay. So if you observe either NMOS case or CMOS case, the delay is directly proportional to nf tau, right? The delay is directly proportional to nf tau. Already n, you know, previously it is ln of y divided by ln of f into f tau, right? So therefore, to minimize the delay, the denominator value, if you see, if f is assumed as e, it becomes 1. The denominator becomes 1. Therefore, whatever the numerator value is there, that is the delay. That too, that is the minimum delay. So assume f equal to e, so that n equal to ln of y. Since f equal to e, ln of e equal to 1, therefore n equal to ln of y. Okay. So with reference to this, the total delay in case of even number of n stages, if you use, the total delay is 2.5 times en tau in NMOS case, whereas in CMOS case it is 3.5 en tau. Okay. So now tell me, what is the value of f? The preferable value is e, that is 2.7 usually. The value is 2.7, but while implementing in practical way, it is maintained as 3. Okay. So like that you can reduce the delay by the varying the width instead of in the single stage in the cascading model, that too increasing slowly like that. Previously we have seen the diagram. Okay, in first stage case f times, in second stage case f square times, in third case f cube, like that. Okay. So but the number of stages depends on, if the number of stages depends on based on the f value again. Okay. Okay, that is the thing. Okay, so in the next class you can see about the super buffers, how they will reduce the delay and how to improve the speed. Thank you.